Hello everyone, and welcome back to an L582 Modeling and Control Electric Machines and Drives. Last time we were talking about the theory of operation of three-phase induction motors. Such a very important machine to deal with. As we said, that's the workhorse of industry. Most of the electric motors used for all the industrial applications will be of the kind three-phase induction motors. So it's of a vital importance to understand the operation of this machine, its construction and theory of operation, and proceed to understand its modeling, and after that we'll talking about the speed control and the starting of it. So last time we started talking about the theory of operation. The most important thing to understand is how the machine actually works and develop torque to rotate its rotor along with any mechanical load attached to it. Like we said, is how this machine works is like the stator and the rotor. Each member of them have to have its own component of magnetic flux, because the torque that means we developed in the machine here of the kind of excitation torque, because the rotor of this machine is cylindrical, non-salient, so you don't have any torque saliency or saliency torque. So we need excitation torque that needs two components of flux, one coming from the stator and the other one coming from the rotor. So first of all, your stator three-phase winding are connected to three-phase voltage source, and that will force electric current to move into the winding and create magnetic field. Like we said before, because that's the three-phase voltages balanced, applied to a three-phase balanced winding, it will create a rotating magnetic field. You have magnetic poles, north and south poles, rotating around the circumference of the stator by the synchronous speed. Okay, and we just derived how this happens in a whole lecture. You can refer back to it. Okay, so you have a magnetic field coming from the stator, and that's rotating. At the beginning, the rotor winding will be at standstill. That means they're not moving at all. They are seeing rotating magnetic fields, so we'll see it as a time-varying magnetic field. And that's all you need to have a voltage generated, induced on these rotor winding. Okay, and like we said in the construction, because the rotor winding are short-circuited, okay, so this induced voltage will be applied to a short-circuited path, and this will move current into the rotor winding. So you have current moving into the winding, creating magnetic field, and that's the component of flux in the rotor, because like we said, we need a stator field and rotor field. The combination of them will create you the magnetic torque, the electromagnetic torque actually, which is the torque of the machine you want to create. Okay, so the rotor flux coming by induction, okay, from the stator flux, because its origins come by the induced voltage in the rotor caused by the cutting of the magnetic field coming from the stator to the rotor winding. That's why we call it an induction machine, because the rotor flux comes by induction, and that's the second component of magnetic flux needed to create the torque. Like we said, the excitation torque generic equation is like we've seen here. It's the torque of the motor equals K, which is a constant related to the dimensions of the motor itself and its materials, multiplied by the rotor flux cross the stator flux. So that's like we said, we need two components of flux. So the stator flux comes from the three-phase voltage source applied to it, and the rotor flux coming by the induced voltage on its winding, coming by being cut by the time varying magnetic field coming from the stator. Okay, like we said last time, is just we have in the rotor also a three-phase winding, just like the stator. So the induced voltage coming from the stator will be also in a balanced shape when applied to the rotor winding, and this will create also a rotating magnetic field. So you have sets of magnetic poles, set of magnetic poles coming from the stator, and they're rotating at the synchronous speed, and another set of magnetic poles on the rotor rotating at the same speed. Each north pole on the stator will be coupled, meaning magnetically attracted to a south pole on the rotor, and vice versa. And both of them, or both of the two pole sets, the stator pole set and the rotor pole set, will be just magnetically coupled together and just rotating at the same speed. And this will drag the rotor body itself to rotate behind them. And we said last time that it has to be running behind them, so the mechanical or the actual rotor speed is a little bit less than the synchronous speed, which is the speed of the magnetic field of both the stator and the rotor. We said this because if this condition is not met, that means your rotor winding will be seeing no variation in the magnetic field because they will be rotating at the same speed of the magnetic field of the stator. So each conductor in the rotor will be seeing the same magnetic pole or the same magnitude all the time because they're rotating together at the same speed. Okay, it has to be some sort of a relative speed between them in order for the rotor winding to see a change in the magnetic field, and this is the source of the induced voltage in the rotor winding. If this not happening, that means there will not be time variation in the magnetic field seen by the rotor winding, and that means the induced voltage on them will be 0, and this means no current, no magnetic field from the rotor, so you don't have any other component of flux, so no torque, and the machine stops rotating. Okay, so that was a revision for the theory of operation we talked about last time, because that's very, very important to keep in mind. Okay, and I'm gonna start today by emphasizing something that is very important to understand, and I will just go back to saying that. So yeah, that is the theory of operation of induction motor. Okay, and it's continued, okay, after last time. So I'm gonna say that using just a very childish drawing to understand what's happening with the speeds of the magnetic field here and the stator. Okay, so that's the stator body. Imagine that you have carts or cars just rotating. So the stator body here is not moving anywhere because it's just the stator, so it's stationary. Okay, but like we said, the magnetic field of the stator is moving, is rotating around this. Okay, so I'm gonna just assume that is some sort of a guy here on top of this cart, and this guy is just moving here by speed. Okay, so that is the stator field. Okay, this guy on top. Yeah, so we know that the easy parts. The stator body, so the speed of stator body, okay, and it's also the speed of the stator winding, okay, because the winding is a part of the body, you know this. Okay, so the speed of the stator body or the stator winding, both of them equal 0, you know that's a stationary part. By definition, it's not moving anywhere. Yeah, but the stator field, like we said, the speed of stator field, okay, equals the synchronous speed in S, 120 F/P. Like we said before, that's the magic of having a three-phase voltage applied to a three-phase winding, is you creating a rotating magnetic field out of a stationary winding. So the stator winding and body are fixed in position, they're not rotating, they're not moving anywhere, but their field, okay, runs at the synchronous speed. Okay, so the stator body acts like a cart without wheels, like you see in here. It's not moving or something, but this guy here is just running, say, in this direction by the synchronous speed in S. Okay, let's look at the rotor. The rotor, we just had it like a cart, but now it has wheels because the rotor rotates. Okay, so that is our rotor body. Okay, and again, that is the rotor magnetic field here, like a guy. Okay, so that is the whole point to understand. The rotor body itself rotates at the mechanical speed, Nm. Yeah, and this guy, the rotor field, that is your rotor field. Okay, magnetic field, of course. This guy runs here also at another speed. I'll call it NSL, which is the slip speed. I'm gonna talk about it right now. Okay, so the speed of rotor body, which is the same speed of the rotor winding, okay, because again the winding is just a part of the body, is the mechanical speed, Nm. It's not 0 like the stator, because that's the rotor, okay, which is rotating. Okay, and I'm gonna say that the speed of the rotor field, okay, that is the thing I'm gonna talk to you about now. Okay, guys, you remember, like I said, the speed of the magnetic field of the stator is the same as the magnetic field of the rotor. They are coupled together, rotating at the same speed. Yeah, so I'm gonna say this now, and pay attention with me, please. Okay, so the rotor field rotates at NSL, calling the slip speed, okay, with respect to the rotor body. Okay, guys? And this slip speed NSL equals NS minus NM. That's very important to know. We call this the slip speed. And you know, it's how much your rotor is just slipping behind the magnetic field. Okay, guys? So I'm saying this guy here, which is your rotor field, is rotating at this this slip speed with respect to the rotor body itself, okay? So the total speed of rotor field equals this slip speed plus Nm. Why? Because this Nm is the speed of rotor body, okay? That's why I draw it like that, because you're having this guy is running on top of this cart, which is the rotor body, but the cart itself is just running. So how much the actual speed of the rotor field, which is carried on the rotor body, will be the summation of the two speeds: the speed of the rotor body, which is the car that is carrying this guy, and the speed of this guy, which is running on top of the car, but by an additional speed, which is the NSL. Okay, guys? That's why this equals NS, because N slip equals NS minus NM. So by substitution, this will give you the synchronous speed, the same as stator field speed. Like we said before, is the two fields, the rotor field and the stator field, coupled together and running at the same speed, but the rotor body runs at a less speed. Okay, guys? So when I'm asking you how much the speed of the rotor field, you just answer me that is the synchronous speed, NS, the same as the stator field speed. But if I ask you how much speed of the rotor field with respect to the rotor body, it will be the slip speed, which is the difference between the synchronous speed and the mechanical speed of the rotor itself. Okay, guys? That is very important to understand here. That is the main idea of the induction machine. It is just, you know, that the rotor field is coming again. It's the rotor field again as the result of having a three-phase current moving a three-phase winding, so that's rotating at a certain speed, okay? But this speed is just the slip speed. So how much the mechanical speed of the rotor, and this rotating field of the rotor has to rotate a little bit higher in speed just to catch up with the stator field at the same speed of it, which is the synchronous speed. Okay, guys? So that's easy now. The rotor field runs at the slip speed with respect to the rotor body, but it runs at the synchronous speed with respect to the stator body, okay, which is the total speed of it. Okay, guys? Okay, so yeah, so the total speed of the rotor field, that means, with respect to stator body. So if you are just standing on the rotor, seeing the magnetic field of the rotor, it will be running at the slip speed, NS minus NM. But if you're standing on the stator body, you'll be seeing the rotor field running at the synchronous speed, NS, the same as the stator field. Okay, guys? And this comes us to define a very important quantity for the induction machines called the slip. Not the slip speed, the slip itself, abbreviated as S, equals NS minus NM over NS, okay? The numerator here, NS minus NM, is your slip speed, NSL, so it is the slip speed divided by the synchronous speed. This guy is the slip speed, and this is the synchronous speed, okay? Like you know that from this, so the numerator is a little bit less than the denominator, because you know it's the numerator is NS minus NM while the denominator is NS, okay? So this slip value is less than 1, and let us say that is only for motor mode, yeah, we're more concerned about the motor mode of this machine, but when we're talking about the generation mode of it, it will change a little bit. But for now, no for this. So the slip is less than 1 because the mechanical speed is less than the synchronous speed, okay? The mechanical speed is the speed of rotor body and winding, of course, while the synchronous speed is the speed of stator and rotor fields. Okay, guys? So this slip quantity is very, very important to know, yeah? And this comes you to define actually the frequency of the rotor, yeah? So the frequency of induced voltage and current, of course, in rotor winding, okay, I'm gonna call it FR, which means F rotor. F rotor, guys, will equal the slip S multiplied by the frequency of the stator winding, okay? So that is FR means frequency of rotor winding, current and voltages I and V, and Fs is the frequency of stator winding, current and voltage. Okay, guys? Why I'm saying that? Because now we can understand what I said before by this, the differences in the speeds, okay? So from this you can calculate the speed of rotor field with respect to the rotor body, okay, by knowing this frequency we said about here. This will equal 120 F over P, because again it's a rotating magnetic field like we said before. But which frequency? It's the rotor frequency, because that is the rotor field, yeah? So this is your slip speed, yeah? Because we said that the speed of the rotor field with respect to the rotor body is the slip speed. So the slip speed equals 120 F rotor over P, which is the number of poles, okay? So like we said, the speed of the rotor field with respect to the rotor body equals the slip speed, which is basically ns minus nm. So it can be calculated from both of those. If you know ns and nm, so it's the slip speed ns minus nm. If you know the frequency of the rotor, calculate it from the regular equation of the speed of magnetic field, which is 120 F, which is the frequency of the voltage or current causing this magnetic field, divided by the number of poles. Okay, guys? That's why we know it. Okay? But don't just forget this. This is the speed of the rotor field with respect to the rotor body. Okay? The total speed of rotor field, again, equals, again, it is the slip speed plus the mechanical speed of the rotor itself. And you know the slip speed can be calculated even from this ns minus nm, or from this 120 F rotor over P. Okay, guys? But what about the mechanical speed of the rotor itself? How to just find it? Okay, keep that in mind all the time, guys. The speed of most of the motors, apart from the synchronous motor, is just related to the load, which is just putting on the rotor. Okay, guys? So when you trying to quantify the actual speed, look at the loading, the mechanical loading on the shaft. Okay, so your shaft of the motor, just like that, you have in this direction tau m, which is the motor developed torque. It is how much torque your motor is creating to drive the shafts and the load in a certain just direction. So the motor torque in this direction, that means the omega m or nm, the speed of the motor, is just going in this direction. But the load torque will be acting in a counterpart like this, like a brake on a car, like we said many times before. So here's the idea. What happens if the load on the motor goes up? Yeah? I don't want to say just it's mechanical loading because we're talking about a motor here, guys, okay? So if the load goes up, attach it to this shaft, whatever this load is. If it is a fan, a pump, any kind of industrial system you're trying to drive, if the load goes up, that is translated that this load torque is going up. So the brake on the shaft, this guy goes up. And this means the speed goes down. Yeah? Remember, like we said before in synchronous motor, the synchronous motor, very, very good advantage is its speed does not change with the change on the load, but it's something just unique for the synchronous motor. Most of the other motors, including the induction motor, the speed actually goes down with the increase in the load. So when the load goes up here, which is its torque load goes up, the mechanical speed goes down. So the rotor speed goes down. It is braked a little bit. Okay? So all the time we are referring back to the slip S, which equals ns minus nm over ns. Yeah? Like we said, when the load goes up, the speed goes down. This mechanical speed goes down. And it's subtracted from the synchronous speed on the numerator of the slip. That means the slip goes up with the increase on the load. So that's your way to quantify the increase in the load. Look at the slip all the time. If the slip goes up, that means you have more load. Because basically the slip represents how much your rotor actual speed or mechanical speed is just slipped behind the synchronous speed or the speed of the magnetic field. Okay, guys? So that is the whole point here. If the slip goes up, and you know that the frequency of the rotor winding equals SFS, like we said before, so the increase in the load, the slip increases, and that means the frequency of the rotor field is just goes up. Yeah? And what does it mean? That means the NSL, the slip speed goes up, because remember the slip speed equals 120 F rotor over P. So the increase in this F rotor, your slip speed goes up. Okay, guys? Remember, the speed of rotor field, yeah, equals Nm plus N slip, the mechanical speed of the rotor, which carries a magnetic field, and the speed of the magnetic field of the rotor itself with respect to the rotor body, of course. So like we said, with the increase in the load, this slip speed goes up and the mechanical speed goes down. So like you've seen here, the speed of the rotor field, the total one, remains constant, remains at the synchronous speed. And that's the whole point of this, guys. So with the increase in the load, Nm goes down and N slip goes up. So their summation Ns remains constant. Like we said before, is the rotor field and the stator field are magnetically coupled together and running at the same speed, which is the synchronous speed all the time, whatever the load is, okay? The load affects the mechanical speed, which is the speed of the rotor, guys. So refer back to the, remember, here is the car we're talking about, that is the rotor body, okay? But here is the magnetic field of the rotor here running on top of it. So this guy is running by Nm, and this guy run on top of the car by N slip, yeah? So when the load comes in, it increases the brake on this car. It tries to hold it off. So this mechanical speed goes down. But while this happens, the frequency of the rotor field goes up and the slip speed goes up with it. So still the summation of them equal the synchronous speed all the time. And this is the very, very important advantage of this motor. So the induction motor can handle the load like this. Its mechanical speed can decrease with the increase of the load, okay? But the motor will not lose synchronism. It will help like that. Remember when I've talked about the synchronous motor, I told you like that, is with the synchronous motor, yeah, the speed does not drop with the load. But with the increasing in the load until a certain point, the motor can lose synchronism. It will break, okay? Induction motor handles this with a different way. Is with the increase in the load, the mechanical speed goes down, but that means the slip will go up, and with the increase in the slip, the frequency of the rotor current will go up with this, and this will increase you the slip speed, which is the speed of this guy on top of the cart, and the cart is the rotor body. Okay, guys? And remember, the total speed of the rotor field is the summation of those two speeds, NSL and NM, the slip speed and the mechanical speed. With the reduction in the mechanical speed caused by the increase in the load, the slip speed goes up, so their summation, which is the total speed of the rotor field, remains constant. Okay, guys? I hope you remember that. So all of those relationships or good relationships, keep those in mind, because it will help you a lot solving any numerical example or understand the operation of any kind of induction motor. Okay? So starting from this, those are all very important relationships to keep in mind all the time. Okay, guys? Okay. And speaking of all of this, and speaking of relationships, and now we are quantifying things, so we can just keep on going with this, and let's talk now about the equivalent circuit modeling. Okay? Just like we did with any other machines, DC machines and synchronous machines, and now the induction machines. We first understand the construction of the machine and understand the theory of operation, how the machine works, and jump to talk about the equivalent circuit modeling, how to model the machine, quantify it, and predict its performance using just equivalent circuit, solving it like an electric circuit, and just see how this machine will perform at different operating conditions. Okay? So again, because it's a three-phase machine, but it is balanced three-phase machine, so this equivalent circuit will be per phase, just like with synchronous machines before. Okay, guys? So I'm gonna just draw you the per phase equivalent circuit of the induction machine of the three-phase induction motor, and we'll start looking at it. Okay, guys? So I'll start here from the stator. So your stator field is just represented by R1, which is the resistance of the stator, and an inductance like before in synchronous machine, JX1. Okay? And here applied V1, which is the stator voltage. Okay? So the voltage applied to the winding, and you will lose some of this voltage as a voltage drop on the impedance of the stator winding itself, which is the resistance R1, and the impedance of the winding, which is X1. Okay? And you will have as a representation here another resistance, we call it RC. Okay? So let me just remind you what's those here. So V1 is the stator per phase voltage. Okay? That is the voltage applied to the stator winding from your supply, but because we're talking about a per phase equivalent circuit, so everything here is per phase. Okay? R1 plus JX1 is your stator impedance. Okay? That is the impedance of the stator winding. Okay? So stator impedance, or let me say it's stator winding impedance. Okay? It's all per phase, yeah? By one phase. RC here, guys, that resistance is the resistance representing core losses. Remember the core losses? That happens in any AC machine because you have eddy current and hysteresis in the field on the core of the machine caused by the variation of the time variation of the magnetic field. So you have a resistance because when you want to just model any power loss, you just model it by the resistance. Okay? So that's a resistance representing your power loss in terms of core losses in the machine. Okay, guys? And another one, guys, here is with a parallel to it. It is JXM. It's another impedance XM. This impedance here is the magnetizing impedance, okay, of the core. It is representing the magnetic field that is just moving inside the core to magnetize it. Magnetize it means just the core itself is now turned into an electric magnet, like we said before. If you remember in your any circuit courses, any coil you have will be represented by an R and an L. This L is the magnetizing, okay? So you have here something representing the magnetic field magnetizing the core itself, and it's a JXM, okay? So both of those, we call this the shunt element, because those are connected in parallel like this, shunt elements, and those representing the core. Why? One of them representing the core losses, the losses that happen inside the core, and the other one representing magnetizing the core. How much, or just, yeah, it's representing the magnetic field that turns the core into a magnet. Okay, guys? That is the stator, okay? And the rest is just going to the rotor. I'm gonna just have this like that. That's a transformer, like you said before with the transformers, okay? Why? Because actually the stator and rotor of the induction machine just looks like a transformer winding, the primary and the secondary winding. Remember the transformers you took before in your courses? The transformer, just you having two winding, a primary and the secondary, and the voltage in the secondary coming by induction from the primary side. Doesn't this remember you anything? It is the induction machine. The magnetic field in the rotor comes by induction from the stator, okay? So it looks like a transformer, but now its secondary winding of the transformer, which is the rotor here, is rotating. So that's why we call induction machine a transformer with rotating secondary. Your transformer have a primary winding and a secondary winding, and the secondary winding field comes by induction from the stator winding, from the primary winding, yeah? They're the same like induction machine. Imagine that the stator is your primary and the rotor is your secondary, and the voltage that is induced in the secondary comes by induction by the induced voltage coming from the magnetic field of the primary winding, which is here in the induction machine is your stator. So it will be represented just like a transformer. So the transformer we're talking about here, it is primary winding at the stator winding, and it is secondary winding it is rotor winding. Okay, guys? Again, the same idea. The voltage is going to the rotor winding. You will lose some of it on the impedance of the rotor, which is JXR. I'm gonna call it JXRO, and I'm saying why now? JXRO or XR0 actually. And here's now a resistance also of the winding, which is R rotor. Okay, guys? So it's again those guys here, R and X, are the impedance of rotor winding. Okay? And you have induced voltage just like the transformer, guys. So here I call this E1, which is the induced voltage at this primary winding of the transformer. So this is your transformer representation. Okay? And this will be transferred from this guy to this guy, and this now the induced voltage on the other guy, we call it E rotor, but I'm calling it E rotor 0 also. Why I'm saying that's either 0, I'll just explain in a minute. But now that is the complete or the whole equivalent circuit of the three-phase induction motor. Okay, here is your stator representation, or the primary winding of the transformer, and here represents your rotor or your secondary winding of the transformer, and the transformer itself is between them here. Okay, guys, so the power comes from here. The electric power goes to the stator like this, and you start losing some of it on the stator. The rest is transferred to the rotor here, where it's just converted into mechanical power as a torque on the rotor. Okay, guys? Okay. Okay. In order not to confuse you for now, I'm gonna say this. I'm gonna just remove those zeros here. So for now, just to keep going is like you see in here, like I said, it's just you have a rotor side and the stator side, and here is the voltage of the rotor side ER, which is induced from the stator, and we know that. And there is a current here, I rotor, which is a current moving inside the rotor winding here, okay, and this is the resistance of the rotor, R rotor, and JX rotor, which is the reactance of the rotor winding. Okay, guys? Now I'm going to explain what those O's and stuff I just took out. Okay? So any kind of machine, guys, will have two states to represent. Okay? So I'm going to start by talking about this machine at standstill. Okay? Which means standstill means no speed. The mechanical speed equals 0, which is also the same as the starting condition. Okay, which is the machine, it's still at starting. That means it didn't move. Okay, guys. At this condition, if you wanna the slip for the machine, which equals ns minus nm over ns, now this mechanical speed equals 0 because you're at standstill. So the slip equals 1. Okay. Remember how to calculate the frequency of the rotor voltage or current, which equals the slip times the frequency of the stator. Now the slip equals 1, so this equals the frequency of the stator winding itself. So the rotor winding at the starting or at standstill, when the rotor is not moving, the frequency of it is the same frequency as the stator, because basically the slip equals 1. Okay? And at the standstill, the voltage induced in rotor winding, we're gonna call it E rotor, 0. Okay. At the same time, the reactance of rotor winding will equal X rotor 0 also. Okay? Why this? Because both of those just depends on the speed. This reactance depends on the speed. Why? Because you remember any reactance equals 2 pi F times L. Okay? And because you're talking about the rotor, that means it is F of the rotor. And F of the rotor, guys, changes with the change in the speed. Why? Because F rotor equals SF stator, yes? So it depends on the slip, and the slip changes with the change in the speed, because the slip equals ns minus nm over ns. So any change in the mechanical speed changes the slip, and this changes the rotor frequency, and this changes this reactance, this X term of the rotor winding. Okay, so this reactance of the rotor winding changes with the change in the speed. So its value at the standstill at 0 speed, will have a certain value, which is XR0. Okay, and the induced voltage on the rotor winding also depends on the speed. Remember when I said if the mechanical speed of the rotor is the same as the synchronous speed, the induced voltage will be 0, because the winding of the rotor will be seeing no change in the magnetic field, and this means the induced voltage will equal 0. So the induced voltage of the rotor winding depends on the relative speed. Okay, keep that in mind. E rotor, the induced voltage of the rotor winding, depends on the relative speed of stator magnetic field and the rotor winding. Okay, because like we said, this induced voltage depends on how much change in the magnetic field seen by the rotor winding. Okay, and while the stator, or the magnetic field coming from the stator, which is the primary magnetic field, like we said, just rotates at the synchronous speed and s. So how much speed on the rotor winding, how much speed of the rotor itself, will determine how much induced voltage you have. Okay, so at the very beginning, this relative speed is very big. This relative speed is very high, and with the rotation, this relative speed goes narrow. So let me talk about the other thing at running condition. Now the rotor rotates at a mechanical speed which is Nm. Okay? How much induced voltage you will have now on the rotor E rotor equals the slip times the value at standstill. Okay, guys? Because like we said, this induced voltage ER depends on the relative speed between the rotor winding and the magnetic field speed, which is basically the slip speed. Okay, guys? So with how much difference in this speeds, how much this relative speeds happens, with the increase in the relative speed, this induced voltage goes up. This relative speed is the slip speed. Okay, guys? With the reduction in this relative speed, this induced voltage goes down. So that means it depends on the slip, like we're saying here. Okay, guys? That's because, like I said, this relative speed determines how much change in the magnetic field seen by the rotor winding, and this change in the magnetic field is the source of the induced voltage from Faraday's law. Remember? Thus, the induced voltage E equals minus N d phi by dt. Okay? So, with the increase in the this time derivation of the magnetic field, and that means how much time change happens in the magnetic field, it determines the induced voltage, E. Okay, guys? So that's why I'm saying this induced voltage here, ER or E, depends on the relative speed between the magnetic field and the rotor winding, because this relative speed determines how much change in the magnetic field seen by the rotor winding itself. Okay, guys? That's why I'm saying that is the actual induced voltage in the rotor, and any running condition will equal the slip multiplied by this value at standstill. And that means that, you know, at standstill, at no speed at all, it is the biggest relative speed, because now the speed of the winding of the rotor is just 0, and the speed of the magnetic field is ns. Okay, guys? So let me say it like that. So here is the magnetic field of the stator going that way and the synchronous speed. While the rotor winding, now here's you have a rotor winding on this guy, so you have just a rotor winding, and the rotor is not moving at all. It's now at standstill, say it, and Nm equals 0. Okay, guys? So any winding, so this winding here on the rotor will be seeing a very much change in the magnetic field of the stator, because it's just running at a very high speed now, at the synchronous speed. And that means you have a very high induced voltage, which is ER0. But what happens if now this speed is not 0 anymore? That means this guy starts rotating here. Those windings start rotating in the same direction by the speed Nm. Okay? That means this relative speed between those guys and the magnetic field of the stator starts to shrink, starts to be less and less. And that means this change in the magnetic field is now go less and less, and that means the induced voltage go less and less. And that's why we have this relationship. That's the induced voltage in the rotor equal the slip times the induced voltage at the beginning, which is a very high value, but with the increase in the speed, this induced voltage goes less and less. Okay, guys? The same idea will be with the X. The reactance of the rotor winding will also equals S times its value at the beginning. Because again, it dots depends on the rotor frequency, and the rotor frequency depends on the slip. Okay, so the frequency of the rotor starts very high, equals the stator frequency, just here, like you see in here. Fr equals Fs, because the slip equals 1. But with the running condition, the frequency of the rotor winding, which equals Sfs, now this slip does not equal 1, because you have a speed now. Nm does not equal 0. Okay, guys? So that's what I'm saying. Fr will equal Sfs, and if you remember, Fs here is your F rotor at standstill, at 0. So that means equals S of F rotor at standstill, F rotor 0. And you know that the S equals, any X equals 2 by FL. So that's how we land to this relationship. X rotor equals the slip times X rotor 0. The 0 just stands for the standstill operation. 0 speed, I'm saying. Okay, guys? Sounds good. So keep those in mind, and let's go back here to see how to quantify the rotor current. Seen here, that is the rotor current, IR. L equals this voltage, ER, divided by the impedance of the rotor, which is RR plus JXR, just like any other current in any circuit. Okay, guys? So, I rotor will equal E rotor divided by R rotor plus JX rotor. Okay, guys? Substituting from those equations, E rotor equals the slip times E rotor 0 divided by R rotor plus JX rotor, which is the slip. Okay, times X rotor 0. Okay, guys? So I'm dividing the numerator and denominator by the slip, and this gives you E rotor 0 divided by R rotor divided by the slip plus JX rotor 0. Okay? From this, guys, so your rotor current can be represented even those or this shape, E rotor divided by P rotor, or sorry, R rotor here, not P, plus JX rotor, or it will be the same as E rotor 0 divided by R rotor over the slip plus JX rotor 0. Okay, that's why we can just, rather than having the equivalent circuit like this, using this value XR and RR and ER, will be just having the same thing or having the same effect if it's like this. That is R1 plus JX1. The stator does not change here. We're not playing with the stator quantities, so that is RC JXM. Okay, and that is your transformer representation. And now here that is your reactance, but now JXR 0, not XR. And this the resistance, but now it is R rotor divided by the slip. It's just like here. Okay, guys? And this will be E rotor 0. And this is your I rotor. Okay? So representing the rotor circuit like this will be just giving you the same exact current like if you represented like this. Okay? By both the running condition or the standstill condition, whatever it is. Okay, guys? They are equivalent. Like we said here, the rotor current will be like this or like this. Okay? Why I'm doing this? Because if this is a transformer, I just want to treat it like any other transformer. Okay? And do what we call the referring of the values. Now let's refer values from the rotor side to the stator side to get rid of this transformer for good. It will be much easier to handle this circuit and deal with it without this transformer in between. Okay, guys? So we can refer those quantities from this side to this side. And that's why we like to do with the 0 at standstill, because the regular transformer happens at standstill. The transformer in any power system does not rotate. The transformer does not have a rotating member. So that's why we just did this transformation and used those 0 values at standstill to be able to refer to those values from the secondary, which is the rotor here, to the primary, which is the stator, and get rid of this transformer. Okay? And that is what will happen now by referring rotor quantities to stator side, you will get rid of this transformer and your equivalent circuit will look like that. It's R1 plus JX1, which is the stator, we're not playing with it, RC JXM, and now we get rid of the transformer and we have now the reactance of the rotor JX2 and the resistance R2 over the slip. And now there is no this transformer. This transformer now is cancelled. But this happens only if we did this referring of the rotor quantities to the stator quantities. Okay? How to do this is just like any transformation happens with any transformer. If you remember with transformer courses before, or when you just studied transformers. So R2 is your referred value, which is equals A squared times the actual resistance of the rotor, R rotor. And this X2 we're using now equals A squared times X of the transformer, XR0, the actual one. With A is your transformation ratio, or turn is ratio, okay, which equals N of the stator divided by N of the rotor, okay? N is basically the number of turns, okay? So if you know the number of turns of winding of the stator or number of turns of the rotor, you can just transfer it like that. Get the actual resistance of the rotor winding and multiply it by A squared. It'll give you the referred value of the resistance, and multiply the X or the reactance by A squared. I will give you the referred value, which is X2. Okay guys, and now you can use this equivalent circuit easily. Now we don't have this transformer in between here, which makes stuff complicated. Now we can deal just like any other ordinary circuit. Okay guys, here is your V1, which is the voltage applied to the stator, and the current moving in the stator, we call it I1. Current going to here, call it IC. Current going there, we call it IM. And the current going here, the rotor current, which is I2. Okay? By the way, this also will be this current, rotor current, referred to stator, okay? So if you want to find the actual current, you should refer it back to the rotor, okay? But we'll not play with this as much, okay? Because we can deal with those referred values all the time. I will just be fine with this, okay guys? Okay, so I know it's a little bit complicated compared to the DC machine and synchronous machine. It's how induction machine works actually. So the modeling and analysis of induction machine is a little bit more complicated because, like we said, all the rotor voltage and currents and fields and everything is just coming by induction from the stator, and that's complicated stuff a bit, okay? So just take time to digest this, okay? Go over it once and once more and you will just understand what's happening. And as usual, I'll be very happy to answer all your questions, okay? Okay, that's it for today. Thank you so much for joining me. Take some time to understand this once and once more, and feel free to ask any questions. I will be happy to answer them. Thanks so much, and see you next time.